Okay, so whenever we have that curvy position versus time graph line, that means we're accelerating. A curved line means slope is changing. Well, that means our velocity is changing. Or the rate at which we're changing position is increasing, right? Slope was rate of change for position. The change in rate of change of our position, that's a terrible sentence, is velocity. So in other words, acceleration is a change in velocity over time. So velocity is a change in position over time. Acceleration is a change in position over time, or a change in velocity over time. So acceleration is delta v over t, which is the same thing as saying vf minus vi over t, right? However much our velocity change in that period of time, that will give us our acceleration. So because velocity includes direction, changing direction means that the thing is accelerating. Speeding up means you're increasing velocity. Slowing down means you're decreasing velocity. And in either of those cases, our slope is going to get more steep or less steep. Okay? So that is the definition of acceleration. It is the rate at which something is speeding up. And we're going to measure this in units of meters per second. So we're gaining, I'm sorry, excuse me, forgive me. It is meters per second, forgive me. Same thing as saying meters per second squared. Basically, every second we are gaining or losing some amount of velocity in meters per second. So our velocity measured in meters per second is getting divided by seconds because every second we are gaining or losing some amount of velocity in meters per second. So meters per second squared is the unit for acceleration. Okay, so let's take a look at my situation again over here. My thrown ball example. I'm going to mark my positions again. So it leaves my hand right about here. It's going up right about here. It ends right over here. So let's go ahead and mark down what we had last time as well. This is my increasing x direction. I'm going to call this position where I started x equals 0. This is my initial point. This is my final point. And here I'm going to look at 3 points on my graph again. So here's this one. Sorry. Here's this one. I'm going to call it point 1. This one. Actually, let's do 1 here in the middle. Point 2. Point 3. Point 4. And then our final point over here. Our initial point over here. I'll call that 0. I'll call that F or 5. 5. Okay. So last time we evaluated our position at each of these spots. We also kind of eyeballed our velocity in these spots. Let's take a look at what's going on here. So here, let's watch the speed of this ball. I want you to watch this and think about it for a moment. At which of my points is it moving the fastest? At point 0, point 1, point 2, point 3, point 4, or point 5. Watch the next loop of this GIF and tell me where you think this ball is going fastest. Okay. It is point 0 where it's going fastest. The moment it leaves my hand is where its speed is the highest. So it's got a longer velocity vector here. Over here, it's curved this way a little bit and it's slowed down. But let's keep this to one dimension. We're just going to say it's slowed down. We're going to ignore the movement left or right. Here, we're just going to look at it in this direction. So our velocity at point 1 has slowed down a little bit. Our velocity at point 2 is actually much slower. Try to look at the distance between 0 and 2. Notice it's going way slower here. And then at 3, its velocity is 0. At 4, its velocity is going down like this. And at 5, right before I catch it, it's got a higher velocity going down. And by the way, if I wanted to name these properly, I'd call that V0, that V1, this is V2, that's V3, this is V4, that's V5. Velocity at each of those points in time. Okay. So if I have the highest velocity pointing up, and then it gets slower, stops at the top, then starts getting faster and faster pointing down, we know there has to be an acceleration. This object's velocity is changing. And which direction is it changing? It is accelerating towards the ground. So at each point in this movement, it is accelerating towards the ground. It's slowing down. This acceleration is acting on my ball the whole time it's going in the air. And we can see that as it loses velocity, loses velocity, loses velocity, stops, gains velocity down, gains velocity down. Every second it is getting accelerated towards the ground. What is the thing that is accelerating it towards the ground? You guys probably already figured it out. It is gravity. Gravity causes the acceleration, and we call an object that is being influenced by the force of gravity being in free fall. The acceleration of gravity on Earth is actually a constant. It is 9.8 meters per second squared towards the ground. In this case, we would call it negative, because I'm calling this direction positive. That means anything pointing down has to be negative. So these velocities are positive here. That one's 0. These are negative. Okay, so we have an acceleration being caused by gravity in this case. Again, objects in free fall is something being pulled to the ground by gravity. It's technically defined as an object that only has gravity acting on it. We call that free fall. Cool. Okay, so just the same as how we can graph a position versus time to give us velocity on the slope, we can graph a velocity versus time. That slope will give us acceleration. Remember, the slope of a graph gives you change in your x-axis versus change in your y-axis compared to changing your x-axis. So if we go position over time, delta x over t is velocity. If we go velocity in time like this, delta v over t, that, my friends, is acceleration. So basically, we can use the slope trick again with a velocity versus time graph. That time, the slope will give us acceleration. So read your axes, and you can figure out what your slope will give you. And likewise, this time we can go backwards as well. So instead of taking the slope to get acceleration, we can go backwards and take distance under the curve of a velocity versus time graph to get distance. So basically, in math, taking the area under a curve is the opposite of the slope. So slope measures change. If you undo that change, you can go backwards too. Undoing that change, the opposite of taking the slope, is taking the area under the curve of the graph. In calculus, by the way, getting a function to give you the slope is called a derivative. And then finding a function that is the area under the curve is called an integral. But we're not worried about calculus. I just wanted to give you those terms. Basically, we can find the area under the curve, and we can get distance from an acceleration versus time graph. Excuse me, I didn't mean to do that. So let's take a look at this. Basically, we know slope will give us acceleration, and we know area will give us distance. Okay, so let's try to solve this problem. Find the average acceleration of this object between the following points in time, kind of similar to what we just did with velocity. T equals 0, t equals 10, 10 and 22, 22 and 30, the whole trip. And then please estimate the total distance traveled over the course of the whole trip. So if you would please pause the video and try to solve this problem on your own. Okay, welcome back. Let's try to solve this. The first piece, let's go ahead and mark our spots. Here I've got t equals 0. My x at this point is like 10, I think. Here at t equals 10, my x is 60. Here at t equals 22, my x is still 60. And then here at t equals 30, my x is negative 20. Okay, so again, rise over run. We're going to find slope the same way we did last time. And we will do that by saying final minus initial position over final minus initial time. That is 60 minus 10 over 10 minus 0. That's 50 over 10, which is 5. So my acceleration is 5 over this point. Here, you actually can already do this in your head probably by looking at the fact that the slope is a horizontal line. And in fact, yes, we get 60 minus 60 over 22 minus 10. That is 0 over 12, which is 0. So the acceleration here at the top is 0. The acceleration for this bit down here, we get x is negative, excuse me, final x is negative 20. Initial x is going to be 60 over t is 30 minus t is 22. And we end up getting negative 80 over 8. The acceleration is negative 10 over this portion of the graph. Okay, and then lastly, we want to find the acceleration between the very beginning and the very end. That is going to be final minus initial 20, negative 20, minus 10 over 30 minus 0. That is going to be negative 30 over 30. My average acceleration is going to be negative 1 for the whole thing. And that makes sense. We have a less steep line between this spot and this spot, but it is negative, just like last time. Okay, cool. So now we found all of our slopes for acceleration. That's great. I'm going to undo all this so we get a better view of our graph. Cool. Now we got to find the area under this curve. So you could find the area under this curve by taking an integral using calculus. But again, this is not a calculus class, so we can do it the old-fashioned way. And hopefully you guys figured out that we can kind of approximate this by breaking this down into geometric shapes. So if you'll notice, this is a trapezoid, this is a rectangle, and this is a triangle. I can break this graph down into geometric shapes and then add their areas together to figure out the total area under the curve. So area of a trapezoid is average of your bases times your height. My height here is 10. This base is 60. This base is between negative 20 and 10 is 30. So that's going to be 1/2 30 plus 60 over, sorry, not over, times your height, 1/2 average of your bases times that is area of a trapezoid. So for this part, it's going to be 30 plus 60 is 90. Half of that is 45 times that is 450 meters. Then this part's a rectangle. I go from 10 to 20. This is an area of 10. Rectangle's area is just length times width. That's going to be 10 times 60 is 600 meters. Then this last part's a triangle. This side has a measurement of 60. This side's between 22 and 30. That's 8. 1/2 base times height is the area of a triangle. So that's going to be 1/2. Your base is 8. That's 4 times 60. 4 times 60 is 120, 240. Okay, so my total area, total distance traveled is going to be 450 plus 600 plus 240, which is 1,050, 1,290 meters. So basically, if I showed you this object's velocity over time, I can tell you how much ground it was able to cover over the course of this trip by taking the area under my velocity versus time curve. And we can do that by approximating geometric shapes. Awesome.